Picture the universe as it was just moments after its birth. Not the vast, star-studded cosmos we see today, but a hot, dense point, smaller than an atom, filled with unimaginable energy. This beginning, often called the Big Bang, marked the origin of everything, the fabric of space and time, the seeds of galaxies, and all the matter and energy that would come to fill the cosmos. But for decades, cosmologists wrestled with mysteries that the initial Big Bang theory couldn't quite explain. Chief among them, why does the universe look so uniform in every direction? Why is space so flat? And how did such minute quantum ripples grow into the galaxies we see arrayed across the night sky? The answers may be found in one of the most remarkable ideas in modern physics, cosmic inflation. Cosmic inflation proposes that, a fraction of a second after the universe burst into existence, a dramatic and incredibly brief period of expansion occurred. Space itself became a rapidly inflating bubble, growing exponentially, much faster than the speed of light. While this sounds like science fiction, the theory of inflation solves several of the deepest puzzles in cosmology and reshapes our understanding of the universe's earliest moments. Consider what happens in that first instant. Just after the Big Bang, the universe is hot and dense, filled with a chaotic soup of energy and particles. But through mechanisms still being explored, a mysterious field, sometimes called the inflaton, takes control. Almost instantly, the universe begins to swell, its size doubling, redoubling, and redoubling again, not over eons, not over years or minutes, but in a vanishingly short fraction of a second. In as little as 1/1,000,000,000 of a trillionth of a trillionth of a second, the universe grows from subatomic scales to something the size of a grapefruit, or perhaps far larger. To grasp the magnitude of this, imagine inflating a balloon not just to fill a room, but to become larger than the observable universe today, all in less time than it takes light to cross a proton. This is inflation, cosmic expansion at its most extreme. But why is such rapid expansion necessary? The answer lies in some striking cosmic conundrums. First is the horizon problem. When we observe the universe in any direction, we find the temperature of the cosmic microwave background, the afterglow of the Big Bang, is astonishingly uniform, varying by no more than a tiny fraction of a degree. Parts of the sky separated by billions of light years shouldn't have been able to communicate. There simply hasn't been enough time since the universe began for light or any signal to travel between these distant regions and even out their temperatures. Yet everywhere we look, the cosmos looks the same. Inflation provides a solution. Before inflation, the universe was tiny enough that all its regions could indeed be in contact. All areas of the early universe had time to shuffle their energy, reach equilibrium, and smooth out any differences. Then, inflation stretches this uniform patch to enormous scales, flinging regions that were once close together far across the expanse of space. The result? Everywhere we look, conditions are remarkably similar because all those places share the same origin. The next puzzle is the flatness problem. According to general relativity, the shape of space can curve. If the universe contained even a minuscule excess or deficit of mass and energy compared to a special critical value, it should have either recollapsed quickly or become wildly curved with time. Yet, observations reveal the universe is remarkably flat, balanced with extraordinary precision on this critical threshold. Inflation solves this too. As space inflates, any initial curvature is stretched out, just as the surface of a balloon looks flatter and flatter as it inflates. No matter what the universe's initial shape, exponential expansion drives it toward perfect flatness, explaining why our universe today appears finely balanced. Inflation also provides an elegant answer to a third mystery, the monopole problem. Certain grand, unified theories of physics predict that the Big Bang should have produced exotic relics, monopoles, super-heavy particles that, if they existed, would vastly outnumber regular matter. Yet, despite decades of searching, no such relics have been found. Inflation comes to the rescue once more. By inflating space so rapidly, it dilutes any primordial relics to near non-existence. The universe becomes so large that any remaining exotic particles are vanishingly rare, consistent with our observations. But perhaps the most beautiful aspect of cosmic inflation lies in its ability to explain the origin of structure. The early universe was almost, but not perfectly, smooth. Tiny quantum fluctuations, microscopic ripples in the fabric of space-time itself, were stretched out by inflation to cosmic proportions. These minute density variations would later seed the formation of galaxies, clusters, and the cosmic web, giving rise to the rich structure we observe today. Think of the universe's beginning as a perfectly calm pond. Quantum mechanics, the physics governing the very small, dictates that even this pond cannot be entirely smooth. Another law of nature ensures that tiny ripples always exist, even in the deepest calm. During inflation, these ripples are magnified terrifically. What was once subatomic in scale becomes vast enough to imprint patterns onto the afterglow of the Big Bang, patterns we have since discovered in the cosmic microwave background. The theory of inflation began to take shape in the late 20th century, advanced by visionaries like Alan Guth, André Linde, and others. Their theoretical work illuminated how a process like inflation could flow naturally from the laws of quantum field theory and high-energy physics. Yet, for inflation to become more than speculation, it needed experimental support. Remarkably, the evidence soon followed. The relic light from the Big Bang, the cosmic microwave background, preserves a pristine snapshot of the universe as it was just 380,000 years after inflation's end. Satellite and ground-based telescopes have mapped this afterglow in exquisite detail, revealing the faint hot and cold spots that correspond directly to those very density ripples inflation predicts. Analyses of these patterns have tested inflationary models with stunning precision, lending great weight to the theory. Moreover, inflation predicts that these fluctuations should have a certain mathematical character, nearly scale invariant, with an almost, but not quite, equal amount of ripples on every scale. This is exactly what we see in the data. It also leads to a universe that should have tiny variations in polarization, minute twists in the orientation of cosmic background light, a subtle signature that cosmologists have been able to detect. But the quest to fully confirm inflation is ongoing. One of the most tantalizing predictions of some inflationary models is the existence of primordial gravitational waves, ripples in space-time itself, generated by inflation's vast energies. These waves would leave a unique pattern on the cosmic microwave background, a faint swirling or B-mode polarization. Hunting for this signature has become an epic pursuit, with experiments on mountaintops and in the polar regions searching for traces of these primordial echoes. So far, the most likely signals of these gravitational waves remain just out of reach, but the search continues. New telescopes, ever more sensitive detectors, and global collaborations are refining their methods and pushing the limits, seeking to catch the universe's whisper from its initial moments. Today, cosmic inflation stands as a pillar of modern cosmology, a bridge between the quantum realm and the grandeur of the universe. It elegantly explains mysteries that perplexed generations of physicists. It offers a mechanism by which the seeds of all cosmic structure were sown, and accounts for the remarkable smoothness and shape of the universe on the largest scales. And yet, profound questions remain. What is the precise nature of the inflaton? How did inflation start? And how did it end? Could inflation be eternal, giving rise to a vast multiverse of bubble universes beyond our cosmic horizon? Some theories suggest our observable universe is but one pocket in an infinite cosmic sea, with inflation continuing elsewhere, forever spawning new universes with their own distinct laws and properties. If true, the multiverse would challenge the limits of our understanding, raising fundamental questions about what can be known and what remains forever beyond our observation. Still, the theory of cosmic inflation continues to inspire, inviting new ideas from physicists, astronomers, and philosophers alike. At the dawn of the universe, less than a heartbeat after its beginning, The laws of physics conspired to create something extraordinary, not just space and time, but the conditions for stars, galaxies, and ultimately, life itself. Cosmic inflation reminds us that the universe is far more strange, beautiful, and interconnected than we ever imagined. Its rapid expansion at the onset of time set the stage for everything to come, the galaxies that shimmer in the night, the intricate web of cosmic structure, and the very possibility for us to gaze into the depths of space and time and to tell this remarkable tale. The journey to understand our origins continues, fueled by curiosity and the enduring human desire to know how everything began. And as we probe ever further, we draw closer to the answers, peering back through cosmic time to the moment when the universe first took its breath and, in a blaze of inflationary expansion, became the cradle for all that would ever exist.